We've been talking about how we go from a sample to learning something about a population that we're interested in. A confidence interval is a range of values that we think contains the true population parameter that we're interested in, and that's what we're going to be going over in today's lecture. Another way of thinking of confidence intervals is as a range of values that the population parameter could plausibly fit into. In our previous video, we talked about looking at taking samples from a population and comparing sample means to the true population mean. And what we found is that when we take a sample of a decent enough size, that sample mean is likely to be pretty close to the population mean. So the sample statistic is a pretty good approximation of the population parameter. But we didn't find in any of the cases that we looked at that our sample mean was exactly the same as the population mean. There is some variability around that sample statistic. So what we're wanting to do is we're wanting to find an interval in which we think that the population parameter actually falls based on the data that we collect in our sample. So let's consider a made-up study as an example to motivate some of our discussion of this concept of confidence intervals. In this study, we take a random sample of 100 college students, and we ask them how many hours per week they spend reading, watching, or listening to the news. So how many hours per week do they spend consuming news one way or the other? In this sample, we find that on average, 1.2 hours per week is how long these students spend consuming news, and we find a standard deviation of 0.61. So we're going to estimate the true average number of news consumption hours per week using the sample data from these 100 students. So the sample mean is 1.2, so 1.2 hours per week, and this is our best guess of the population mean. We use the sample statistic as our estimate of the population parameter, but we're also going to create what's called a 95% confidence interval. So approximately, the 95% confidence interval is our point estimate, 1.2, plus or minus 2 times the standard error, where the standard error, like we talked about in the last lecture video, is the standard deviation divided by the square root of n. So our standard deviation in our sample was 0.61, and n is 100. We sampled 100 students. So we take 0.61 divided by the square root of 100, that's about 0.06. And that is the standard error in our confidence interval formula. So our 95% confidence interval is going to be our point estimate for the mean. So x bar plus or minus 2 times the standard error. So 1.2 is x bar plus or minus 2 times 0.06. This gives us 1.2 plus or minus 0.12, or a confidence interval, a range from 1.08 to 1.32. So let's talk about what this means. How do we interpret this confidence interval? So remember that a confidence interval is something that we derive from our sample data. We create this range of values in which we think a population parameter falls into. So we just calculated this confidence interval from 1.08 to 1.32. Take a look at this question and these different interpretations of that confidence interval and see if you can figure out which one is correct. Is it that the average number of hours per week that college students in this sample spend consuming news is between 1.08 and 1.32 hours per week? Is it that college students on average spend between 1.08 and 1.32 hours per week consuming news? Is it that a randomly chosen college student spends between 1.08 and 1.32 hours per week consuming news? Or that 95% of college students consume between 1.08 and 1.32 hours of news per week? So take a minute and see if you can figure this out based on the information that we've talked about so far. The correct answer is that we conclude that with 95% confidence, college students on average spend between 1.08 and 1.32 hours consuming news every week. So we're taking the information that we have from our sample and we're making a generalizable statement about all college students. So let's take a minute and talk about why these other options are incorrect. Option A says that the average number of hours per week college students in this sample spend consuming news is between 1.08 and 1.32. This isn't the right conclusion because this is only talking about the students in our sample. We already know what the average number of hours per week the students in our sample spend. It's 1.2 hours per week. So we don't need this confidence interval to tell us about our sample. We already have the sample statistic. What we're wanting to do is make a general statement about the population. Option C says that a randomly chosen college student spends between 1.08 and 1.32 hours per week consuming news with 95% confidence. This is incorrect because it's a misinterpretation of what the confidence interval is around. So the confidence interval is an interval around our estimate of the population mean, so where this distribution is centered. It doesn't tell us anything about the dispersion of the data around the mean. So we don't know for sure that 95% of the data is clustered between 1.08 and 1.32. That's not what the confidence interval is telling us. The confidence interval is giving us a good estimate of the center of the distribution, but randomly chosen college students might watch way less news, they might watch way more news. We would need other information about the distribution, like its variance, to be able to make a statement about what randomly chosen college students are likely to fall in a particular interval. And this final option, option D, says that 95% of college students consume between 1.08 and 1.32 hours of news per week. This is basically the same error as option C. We don't know that 95% of college students are within this particular range in the population. Our confidence interval is giving us information about the mean, not the rest of the shape of the distribution, how all the other college students fall out in terms of their news consumption habits. So let's say that we took lots and lots of samples from our population, and we took each individual sample and then calculated its mean and then the standard deviation around that mean, and used that information to calculate our confidence interval for each of our samples. What the 95% confidence interval means is that when we take those repeated samples and construct the confidence interval that way every time, about 95% of those intervals would contain the real population mean mu. So when we take lots and lots of samples, construct lots and lots of confidence intervals, if we construct the confidence intervals in order to have 95% significance, that means that 95% of them about are going to have the population parameter that we care about. So in this example, we are seeing confidence intervals for 25 different samples. The actual population mean that we're interested in is this dotted line down the middle, and each of the blue horizontal bars represents a confidence interval. And in the middle of those confidence intervals is the sample mean. So we can see that for most of these blue bars, they overlap the true population mean. That means that the actual population mean is somewhere inside that confidence interval. So some of these sample means are farther away from the population mean than others, but the majority of these samples, and for the majority of these confidence intervals, the real population mean is somewhere inside that interval. And we have this one red horizontal line that is off to the left of the population mean line. This is our interval that does not contain the population mean. So this is an interval that's a little too far away. And that interval doesn't contain the real population parameter. We're not guaranteed that our sample and the confidence interval that we take from that sample is actually going to contain the population parameter. The best that we can do is set a certain confidence level and say that we expect that most of the samples that we draw this way will contain the real population parameter. We've been talking about 95% confidence intervals. That means, again, that if we take repeated samples from our population, construct confidence intervals by that formula for every sample, that in 95% of those confidence intervals for those repeated samples, the actual population parameter is going to be contained in it. We don't have to set a 95% level of confidence. So I'm giving you a general formula here for confidence intervals for any confidence level. So we're going to set our confidence level based on this variable z. We're going to talk about some examples of this in a little bit, but I wanted to go ahead and give you this general formula. So here's a question to see if you're understanding the intuition of the confidence interval concept. If we want to be more certain that we capture the population parameter, if we want to increase our level of confidence, should we use a wider interval or a smaller interval? Well, our interval should be wider. If we want to make sure that our interval contains the real parameter, we should stretch out the bounds of that interval to encompass more and more values. This is an amusing cartoon that illustrates this point, I think. Garfield is watching a weatherman who is saying that the high temperature for tomorrow is going to be between 40 below zero and 200 degrees above zero Fahrenheit. And Garfield's comment is that, well, this guy's never wrong. This is going to be a pretty wide interval in which the temperature can fall into. And the weatherman is certainly correct that the temperature for tomorrow's weather is going to be in this interval. The problem is that's not very informative. So there's a trade-off between how certain we are that the real population parameter falls in our interval and how precise we are and how informative that interval actually is. So it would be a lot more useful for me to tell you that the temperature tomorrow is going to be between 70 and 75 degrees Fahrenheit than for me to tell you it's going to be between -40 and 200 Fahrenheit. I'm more likely to be correct if I give you the wider confidence interval, but you're more likely to be able to plan your outfit if I give you the smaller confidence interval. So there's a trade-off involved. So let's say that we want to be able to pick our confidence level. I already introduced this formula to you. In general, the formula for our confidence interval is our point estimate plus or minus a number z times the standard error. So for a confidence interval, z times the standard error is our margin of error, and the margin of error is going to change based on the confidence level that we pick. So to change our confidence level, we need to adjust this variable z. And we're going to do that by looking at a standard normal or z distribution. So we used z tables already in some previous examples, and we're going to continue using those normal tables as we decide on our confidence levels. In practice, commonly used confidence levels are 90%, 95%, and 99%. But of course, you can pick a confidence level however you please. If you want a 90% confidence level, we're going to look in a z table for a probability that's going to correspond to this confidence level. So let's do a quick example of this. So when I look at these distribution tables, these normal probability tables for my z-scores, what I'm looking at is a level z that corresponds to a particular percentage of a distribution that falls below that point. When I set a confidence interval, what I want is for the bulk of my distribution to correspond to my level of confidence. So at a 95% confidence interval, 95% of my observations fall in the middle of the distribution, and 5% of my observations are out in these extreme tails to either side. So we have to do a little bit of mental gymnastics here to go between the normal probability table, which chops off probabilities at one end of the distribution, to a confidence level that chops off extreme values at either end of the distribution. So if I want to calculate a 95% confidence level, I want to set bounds, so z-scores, that are going to chop off 5% of what remains, right? So if I want 95% of my observations to be in the middle of my distribution, I want to get rid of the 5% at the extreme ends of my distribution. And because the normal distribution is symmetric, I want to divide that in half. So I want to get rid of that extreme 5%. I want to get rid of 2.5% at the low end of my distribution and 2.5% at the high end of my distribution. I'm going to just select a single z-score though. Because the normal distribution is symmetric, I can just select a single z-score. So I'm going to find the z-score that gets rid of the 2.5% at this extreme right end of the distribution. So let's say that I want a 90% confidence level, so I want to get rid of the extreme 10% of observations to the low end and the high end of my distribution. So I take that 10% and I divide it in half. And I find a z-score that lets me chop off the extreme 5% at the top end of my distribution. So here in this table, this is at normaltable.com, I'm going to look in the middle of this distribution chart, and I'm going to find the number that's closest to 0.95, right? This corresponds to getting rid of that 5% at the extreme high end of my distribution, so that I end up with a z-score that lets me get rid of that high 5% and the low 5% to give me a 90% confidence level. So here in the middle of the distribution, I can look at these different proportions here, and I want to find the one that's close to 0.95. So I could pick either 0.9495 or 0.9505. Those are equally far apart from 0.95. It doesn't really matter which one I choose for this example. So I can see when I go to either of these that this corresponds to a z-score of 1.65 or 1.64, depending on which of these I want to use. So I find this observation, and then I follow out my row and my column to find the z-score that I'm interested in. You can do this for any of the confidence levels that we might want to find. So let's say that we wanted that 95% confidence level. So in this case, we want to get rid of the 5% of extreme observations. So we're going to look for a z-score that lets us get rid of 2.5% of the extreme high observations. So that corresponds to 0.975. So this lets me get rid of 0.025 to the high end. So here's 0.975. That corresponds to a z-score of 1.96. That's 0.975. We were approximating that with the number 2 when we were calculating 95% confidence intervals. If you want to be more precise, you would use the z-score of 1.96. So hopefully that makes sense, and you can go and use the normal probability tables to find z-scores for the confidence levels that you're interested in. In the last point in this slide, I have a couple of formulas that might make it a little bit clearer if you're still not entirely sure how you would go about finding the right z-score for your desired confidence level. So feel free to refer back to this in the future as you're working out these problems. So let's go ahead and look at an example here. If we wanted to calculate a 98% confidence interval, which of these z-scores would be the appropriate one to pick? 1.65, 1.96, 2.05, or 2.33. You should pause the video, pull out a z-table, and test your understanding. These concepts can be a little bit complicated, so you really should do this. So for the 98% confidence interval, we want to chop off the most extreme 1% of values at either end of the distribution. So we would want to look in the z-table for the appropriate proportion, getting rid of the most extreme 1% of the observations to the far right side of the distribution. And that's going to correspond to a z-score of 2.33. And that has been our discussion of confidence intervals. Thank you for watching, and I will see you next time.